I now call to order the Society's 2,467th meeting in what is now the 151st year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends, including everyone here in the Powell Auditorium at the Cosmos Club, and everyone tuning in on Zoom and on YouTube to tonight's lecture by Tony Levi. The Society is grateful to the sponsors of the 2022-2023 lecture series for their support, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who's asked to remain anonymous. Please join me in thanking them, and also please join me in thanking the sponsor of tonight's lecture, PSW member Adarsh Deepak. I am pleased to announce the following new member, tonight's speaker, Tony Levi, whose interests will be clear in small part from tonight's lecture. We welcome him to membership. If you are not a member and would like to join PSW or support the Society, you can do so through the PSW website using the blue Join button on the upper right-hand corner of the home page. We welcome new members and we appreciate donations. Please join. All members are entitled to wear the PSW Science Rosette. The rosettes are $15 plus 90 cents DC sales tax, at least this year. They can be purchased online or at the rosette table at the back of the auditorium. Please note that rosettes must be picked up at a lecture here in the auditorium. PSW Science member Janet Surath will now read the minutes of the 2,466th meeting and the lecture by Francis Housen on the Ice Cube Neutrino Observatory on behalf of Recording Secretary James Heelan. Janice, the stage is yours.
Good evening, everyone. Can you hear me? Okay. On November 4th, 2022, from the Powell Auditorium of the Cosmos Club in Washington, D.C., streaming online via Zoom and the PSW Science YouTube channel, President Larry Milstein called the 2,466th meeting of the Society to order at 8:05 p.m. Eastern Standard Time. He announced the order of business and welcomed new members. The minutes of the previous meeting were then read and accepted. President Milstein then introduced the speaker for the evening, Francis Housen, Willis Research and Gregory Bright Distinguished Professor of Physics at the University of Wisconsin-Madison and Principal Investigator of Ice Cube. His lecture was entitled Ice Cube, the Under the Ice Neutrino Observatory in Antarctica, Opening a New Window on the Universe from the South Pole. In 1930, theorist Wolfgang Pauli first proposed the existence of neutrinos, saying, "I have done a terrible thing. I've invented a particle that cannot be detected." Housen said the neutrino's role was to save the laws of physics. In the years following Pauli's hypothesis, scientists confirmed the existence of neutrinos via circumstantial evidence. Neutrinos are detected in nuclear reactions, and in nuclear reactors, neutrinos turn cooling water blue. Housen said the phenomenon is created when a charged particle passes through water and emits blue light. Neutrinos are also emitted by cosmic rays bombarding Earth's atmosphere, making nuclear reactions with nitrogen and oxygen to release neutrinos and muons. Viewing the night sky in infrared reveals the microwave background of the universe. Going to blue wavelengths then reveals a narrow band across the sky, and increasing the blueness eventually results in a black sky image. Halson said that blackness could be explored by detecting neutrinos. That is the research he has sought to conduct. Unlike photons from the microwave background, neutrinos that reach Earth from the edge of the universe carry information about their origin. They are also difficult to detect. To detect neutrinos requires water and light sensors called photomultipliers. The idea of how to do this dates back to 1960, when Moises Markov proposed to build deep in the clear ocean a cubic kilometer of light sensors pointed toward the sea floor. The idea was to detect neutrinos coming through the Earth to collide with a nucleus in the water, emitting detectable blue light and muons from which neutrinos' trajectory can be calculated. Telescopes can then be directed to view the neutrino's origin and watch for an event that may have emitted the neutrino. Halson realized it would be safer to place the photomultipliers in ice rather than in the open ocean where they were exposed to, his words, an unfriendly environment. His idea eventually became IceCube, the neutrino detector installed near the South Pole, where the ice is approximately 3 kilometers thick. He said that 1.5 kilometers below the surface, where the ice is 50,000 years old, it is free of bubbles and perfectly clear. There, blue light travels for hundreds of meters. The speaker then described the IceCube construction and its instruments with photographic aids. The project was initially comprised of 500 photomultipliers measuring 10 inches each, set 1.5 kilometers into the ice. The photomultipliers are organized into kilometer-long strings sunk deep into the ice. Today, IceCube is comprised of over 5,000 photomultipliers set into the Antarctic ice at depths between roughly 1.5 and 2.5 kilometers below the surface. Halson said once frozen, the detectors are completely safe from external harm or interruption, and they've even survived the SARS-CoV-2 pandemic so far. He then showed images and described the process his team used to bore holes through the ice and position the detectors. IceCube detects 100 billion muons per year. Of those, 100,000 are from the atmosphere. From those atmospheric neutrinos, IceCube is searching for cosmic neutrinos. To do so, Halson explained how the project measures neutrino energies and trajectories. He showed animated data to illustrate what it looks like when IceCube detects a cosmic neutrino. It detects approximately 200 such neutrinos every year. IceCube's conclusions thus far are that it detects the universe rather than our own galaxy. In the extreme universe, more energy is emitted in neutrinos than gamma rays, and those conclusions represent an opportunity for a new astronomy. When IceCube detects a cosmic neutrino, the team forwards that data to telescopes around the world to give them the opportunity to look at the neutrino's point of origin. In September 2017, the Master Robotic Optical Telescope Network associated a detected neutrino with a flaring blazar from an active galaxy within the Orion constellation. Earlier on the same day of the lecture, Science published Halson's conclusion that IceCube accurately detected galaxy NGC 1068 as a neutrino source. He explained in depth the process his team used to interpret their data. After he concluded his lecture, Halson answered questions in person and online, and from the online viewing audience. One member asked about the theoretical limit of detector resolution. The speaker said the key is to understand the optics of Antarctic ice, which is an ongoing process. He said glaciology research is a collateral research area for the project. Another member asked about the cost. The speaker said IceCube has currently spent about $300 million and has a proposal to construct a detector 8 times as large for the same amount of money. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein then adjourned the meeting. The temperature in Washington, D.C. was 18 degrees C. The weather, partly cloudy. Attendance then 47 in person and 40 streaming for a total of 87 live viewers and 459 online viewers in the first 2 weeks of posting. Respectfully submitted, Janice Sareth, on behalf of Recording Secretary James Heelan. Thank you.
Thank you, Janice. Are there any comments or corrections to the minutes? Okay. We might add that in relation to the last question, it was pointed out that that was equal to the cost of a relatively small NASA mission. So we now turn to tonight's speaker, Tony Levi, and his lecture on chip scan and ptychography. Tony is professor and chair of electrical and computer engineering electrophysics in the Department of Electrical and Computer Engineering at the University of Southern California, where he has been on the faculty for almost 30 years. And before joining the USC faculty, he was at AT&T Bell Laboratories. Tony invented hot electron spectroscopy, discovered ballistic electron transport in heterostructure bipolar transistors, demonstrated room temperature operation of unipolar transistors with ballistic electron transport, created the first microdisc laser, and carried out work in parallel fiber optic interconnect components in computer and switching systems, among other things. His current research interests include device physics at the classical quantum boundary, design of small electronic and photonic systems, and coherent control of transient dynamics. Tony is an author on numerous technical publications and 5 texts: Applied Quantum Mechanics, Essential Classical Mechanics for Device Physics, Essential Semiconductor Laser Device Physics, and Essential Electron Transport for Device Physics. He also is an inventor in 17 US patents. Tony earned a Bachelor of Science at the University of Sussex and a PhD in physics at the University of Cambridge. All questions will be fielded after the lecture during the question and answer session. Tony, the stage is yours.
Thanks very much, Larry, for the introduction. It's certainly a pleasure to be here. Now, in terms of the talk today, it's something that's to do with technology and how critical technology has become in terms of integrated circuits and in the global economy, where we've got the manufacturing taking place on the, in places other than the United States. We need to have in place mechanisms for understanding the manufacture of chips and being able to reverse engineer without damaging those chips. And that was what inspired this work that started sort of 7 years ago. I can give a little bit of a history on that as we go forward. However, for this evening, there's a lot to learn. And how I go about showing you this is, of course, a bit of a challenge, because it involves multiple threads, multiple aspects, which I'll try to give you a flavor of without getting you lost in sort of minute detail. So let's start off. Today, you know that very sophisticated technology permeates every day of every aspect of life. A good example is the cell phone. The smartphone involves design, manufacture, and a whole ecosystem which has very large number of components that have to be brought together to build the system. And it's not just the physical parts that you see here in the picture. It is also an ecosystem that's built around it. So there are novel materials, special semiconductors, devices, sensors, special circuits, lots of bits and pieces that have to go together and be put together in a way that that everything works and delivers customer, an experience to the user that is both reliable, meaningful, and adds value. There's a lot here, a lot to be taken in, and a very diverse set of technologies have to be looked at. As you'd notice, for those of you who are a bit older, there was, of course, a time before cell phones. That was a more primitive era that we might call BC. So when I talked to my daughter about this, I said, well, yes, there was this other time, BC. And she doesn't know what I'm talking about. So a lot of that is built on the success of integrated circuit technology. And so I show you in the bottom left-hand side here, you can see here a little chip that's an example of leading edge circuit design that we did at USC, and then next to it is the M1 and the M2 chip, also designed in the leading edge technology by Apple, that contain, the larger chips contain billions of transistors. And so how do you know when it's manufactured out on the Pacific Rim, how do you know that the manufacture has taken place according to your original design and that something else isn't in there? So that's going to be one of the ideas that we're going to pursue. And it's an idea that the government was interested in as well. And so we worked a little bit with them, but mainly we brought this forward in other ways. So in terms of effort today, I want you to start understanding numbers. So length scales. And to understand the sort of miracle of the state of the art in integrated circuits, you have to understand these scales. So human hair, which you can actually see, has a diameter of somewhere between 60 and 100 microns in diameter. Now you might say, what causes that range in diameter? Well, it depends on the color of your hair. So those of you who are interested, you can explore who has the larger diameter hair. The human blood cell is about 5 microns in diameter. So you can't really see that easily, a single individual cell, you can't see that so easily. But larger cells are bigger. Now, let's look at something that is very important in technology, which is the glass fiber. So a silica glass fiber, this example here is a Corning called single mode fiber, that's the SMF 28E plus, which is got a 9 micron diameter. That is the little 9 micron core, which is slightly germanium doped. And then the diameter of the actual glass cladding, the glass around it, is 125 microns. That's something, again, that you can see with your naked eye. And in fact, this particular glass fiber has been cleaved. You can see where the scratch mark was made, and then that fiber was cleaved. And then it was imaged in a scanning electron microscope, and that's the image that you see there with the 25 micron marker. So let's try and understand what that size scale is, how it relates to numbers of transistors that can be produced in a given area. So today, using a 0.005 micrometer technology, that means a 5 nanometer CMOS technology, you can get more than 1 million transistors into an area with 100 micron diameter. That corresponds to more than 200 Intel 8080 8-bit processors that were produced in 1974, and that was state of the art back in 1974. So think of that. You can get 200 of those in that face, in that cleaved face of a glass fiber. It's awesome. It's absolutely awesome where we've come from in the technology. Here's another way of looking at it. Along the horizontal axis, you see year on a linear scale, and up the vertical axis, you see on a logarithmic scale, you see minimum feature size of transistor. And so you see, when I started work when I started work at Bell Labs that Larry had mentioned at the introduction, the minimum feature size was 2 microns. This has decreased exponentially over 45 plus years of this decrease in minimum feature size, decreased exponentially, and now we have 5 nanometer a minimum feature size transistors being produced, corresponding to 130 transistors per square micron. Think of that little fiber and the core of the fiber, and then say do something that's 10 times less than the small, 100 times less area than that core you saw. I can fit 130 transistors in that. On the vertical axis here, you see again, this is 6 micron technology that was used by Intel in 1974, had 4,500 transistors and a clock rate of 3 megahertz. And now there's been an increase in the transistor density of of greater than 500,000, an increase in the clock frequency of greater than 1,000, an increase in the word length of 8. So you've got a 10 billion times increase in performance if you just multiply those numbers together. I said this was going to be about numbers. Keeping your brain sharp, think about those numbers. So 5 nanometer technology, the Apple M2 64-bit processor in 2022 has 20 billion transistors in an area of 155 square millimeters and a clock speed of approximately 3 gigahertz. That isn't, of course, the end of the story. The point is, when you have this exponential decrease in minimum feature size, there's an exponential increase in performance. And you saw that here. And that acts as a constraint on the type and scope of innovation that can take place. So you have actually a dramatic improvement in performance that kills certain types of innovation that could take place. That era is coming to an end. You can see in the 2030 timeframe, you will not be able to follow this chart. It will not be able to go beyond 0.001 of a micron. Just isn't going to happen. So something else has to happen, and there's going to be some opportunities going forward. From a national security point of view, in 2020, actually it was obvious many years ago, but the government finally woke up to recognize that the US, shown here with a little American flag, this is in 2020, had a transistor density disadvantage relative to manufacturers that were very close to mainland China. And this turns out to be a threat to national security because you don't know what's going on in countries that are 60 times closer to China than in the US. So these were all concerns, and yet opportunities there to go beyond incremental improvement and a new era of super custom, where there's a time to nurture and transition innovation instead of it being crushed by the old paradigm of Moore's law. Now, given that background, can you trust, do you trust the electronic hardware you use? You ought to be a little skeptical. There's lots of opportunity for malfeasance. There's other types of technology being developed that you might want to investigate and reverse engineer. You'd like to understand more about what is going on 6,000 miles away. And it starts off on a larger scale. Here's a chip that is being packaged in Vietnam from Intel Corporation. And you look at the packaging. This is conventional packaging, and you it's an Intel microprocessor, and you look at what's inside the package without opening it up, without destroying it. And this was work that was done in Switzerland using a medical imaging technology. The size of the sort of size of the voxels used was rather large, so the resolution was rather poor, but you could test at the package level that the connections were correct and that the various support components were in the right place. If you zoom in a little bit more, you can get down to here 6 micron sized voxels and pixels. You can see in more detail the vias that connect various parts of the printed circuit board on the right-hand side, and then some capacitors and so on that are laid out in the on the left-hand side. And you see the length scale is in the millimeter range. Well, we don't want to do this stuff. We want to get down to the transistor level. So let's look at conventional approach to discovering what's inside a chip. Let's look at a chip that's manufactured on the Pacific Rim, and it's a few millimeters on a side, and it's got some solder bump pads on the front surface. How do you find out what the metal interconnect layers are? How do you find out where the transistors are? How do you figure out whether it has been manufactured according to your design? Well, the way that's done currently is a destructive delayering process. You mount that chip that is on the left-hand side, you mount it on a block, as you see on the right-hand side, and then you start grinding through the layers. So it's a destructive mechanical polishing to delayer the chip. The chip is made up of layers that are interconnected with vias, electrical layers, electrical conducting layers that are interconnected with vias. This is a slow process, and you see here I started off with an optical microscope image of the complete chip, 2.5 millimeters on a side, grinding through those layers, looking in a little closer where the solder bumps are, and you go through that, and you can look in the SEM, and you start looking at some higher level metal interconnect. Way down at the transistor level, just above the transistors, is the first metal layer of interconnect. Here it is. You see those railroad tracks running horizontally from side to side? They are 500 nanometer apart. And then the little connections that you can barely see are connecting individual transistors. That's called the M1 layer, metal 1 layer. You go next layer up is called M2, and so on. There's M7 show. The problem with this is you have a chip that you've got. There's only one shot at getting this right. You mess it up, that's it. You can't go back and reinspect. Oops, I was more interested in this. I want to find out what happened. Too late, it's done. So this has lots of negatives associated with it, including you can't go back and redo, including that as the minimum feature size gets smaller, the metal layers get thinner, and so you don't have these pretty pictures anymore. You have to reconstruct pieces which are not planar surfaces, and they go up through multiple layers, and that becomes a real bit of a nightmare. So this destructive delayering process is not optimal. It's slow, and it's for non-planar structures, such as the more modern transistors, it's very difficult to make the reconstruction. So what we want to do is a non-destructive chip inspection using, in this case, coherent X-ray 3D imaging. So we can look at in 3 dimensions what is actually being manufactured. And let's see if we can do that. Well, yes, of course we can. This is an efficient way to do it, and we want to get down to 1,000th the scale that we were doing, the resolution that we were using before. So it's a big step, and this work was published in a couple of years ago that I'm showing you here. Well, I'm going to show you in a little while. This is a work that involved putting together an incredible team of people. I can say a few words about that. Finding the humans and the resources to do this is actually a delicate task. I spent a good part of 2016 traveling around X-ray facilities in the United States and abroad. And after interviewing a number of engineers, came to the conclusion that a facility in Switzerland, a national lab in Switzerland, was the best choice for our team to work on this project. And it turned out to be very good. So Mirko and Manuel were key members of that team in Switzerland. There was also a need to interact with, at that time, current state-of-the-art foundry. And there we went to Global Foundry, and Bill Taylor and Sri Samavedam were key players in giving us access to the technology so that we could work on this project. And you'll see a little bit of that. And of course, people from university that I'm affiliated with were also involved in this effort. So choosing the right team was a very important step. Other people had tried similar things in the past and didn't get the results that we managed. How can you be sure, okay, that the functional and trusted, that the circuit is functional and trusted, has no kill circuits, no counterfeit or malicious and defective parts, manufactured within specification at a given foundry? You can't be sure unless you have a way to measure and make sure that it's actually happened. So here you see the top right-hand side, another picture of USC, the Swiss light source, which is the national lab. I think you should be able to see the synchrotron for the X-ray source here. It should look like a donut that's sort of 100 meter in diameter in that image. And Global Foundries in upstate New York, Malta in New York State, were our key partners in making this happen. Let's talk a little bit about data. Huge amounts of data, petabytes of data per square centimeter. Complexity, many transistors and interconnects at high resolution, greater than 10 billion transistors per square centimeter. Massive need for improvements in algorithms to run the inverse problem to actually establish what the 3D image is from the X-ray data. And if this all worked, we would have a new sort of era where open source hardware is inevitable, because you can't hide anything in hardware anymore, because I'll be able to tell you exactly what's going on inside these chips. And this includes current attempts to try and secure chips by other means. In terms of synchrotron technology, it's an established and mature technology. There's at least 50 such X-ray sources around the world. Notice the very large number in Japan, quite a few in Europe, and of course in the United States. More than 60,000 users. So you're tapping into a knowledge base to get this job done that is, it's not only have you got the best team that you can find, you're also tapping into an ecosystem that can move things along. So in a sort of understanding the next steps, let's start off with ptychographic 3D tomographic reconstruction. A lot of fancy words for something that is, I'm going to hopefully explain rather easily. The traditional way this type of X-ray imaging is done, you have a coherent beam of X-rays, which you focus onto a sample, and the sample is shown here. It's a 10, in this case, you have cut out a 10 micron diameter pillar, and you can see here some metal layers for rather legacy technology system. And you run the X-rays horizontally through these layers, and you rotate the sample with the beam fixed, and you collect diffraction patterns. So coherent X-ray beam diffracts from the metal layers and produces a intensity pattern that is picked up on a focal plane array of detectors that is the diffraction pattern that you see here. So the diffraction pattern at the detector is the two-dimensional Fourier transform of a projection through the sample and corresponds to a cross-section of the 3D Fourier transform of the whole object. Now, the challenge of reconstructing the image the 3D object is the challenge of finding the field and the phase at this plane just given the intensity data. And so this is a inverse problem, and the only way to proceed is to take many such images and rotate the sample and collect the corresponding data, and then do the inverse problem on this. So let me show you, while you're thinking about that, let me show you something in Global Foundries technology that we started working on. So this is showing a similar cylinder, but this happens to be something from Global Foundries. The design is shown here in 3D. So the design is made up of mask layers, photolithographic mask layers, showing here the first few layers in the process of manufacturing a chip. You start off at the bottom and you start working up. And I'm just showing layer 3 through 10, which layer 10 is the M1 layer, the first metal layer above the transistors. You can synthesize all of this and model it by taking the mask layers, knowing the thickness and the materials, and figuring out what the 3D object should look like in a model. We haven't done any X-rays yet, we just created a model. And we're already working quite hard, in case you're worried. This is, it turns out it's a certain type of circuit for testing. For those of you who know about circuits, you'll recognize this immediately. This is the metal 1 layer in the photolithographic mask, and if you take this cut in red and you now plot it out in 3D on the right-hand side, you see what the actual metal in yellow looks like in 3D, and lying below are other parts of the process, including implantation and so on. Now, we can do a fly-through through this cylinder of the synthesized object, and this is what it looks like. So you see I can fly in like an architect flying through a new design. I can fly in through my design in 3 dimensions and look to see for those patterns of metal interconnect on the first layer, and I can see them. I hope you can see them. It may be you think of the Jetsons or something in some cartoon, but this is actual 3D rendering of a design of a transistor circuit. Not the measured case, but the design. So we'd like to now go, knowing what the design in 3 dimensions should look like, we now want to go away and measure it using X-rays, using the method, the established method that I had shown you before. And so this is the result of that inverse scattering problem, and showing you the a fly-through through the same thing. So we go through the upper layers, we dive down towards the lower layers. You look to see the vias connecting metal interconnects. You see those vias, and eventually you get down to the metal layers that contain this is the metal 1 layer. I, of course, recognize it. You may not. And it, given our proximity to Hollywood, you can imagine at USC we had lots of fun figuring out how to generate these videos from the X-ray data after we had done the inverse problem. So this turns out to be the copper metal interconnect in a circuit from Global Foundries, manufactured in a 20 nanometer process that we have there. So not only can you get the 3D image, you can then slice through it and reconstruct the photolithographic mask by taking a layer, in this case the M1 layer, and reproducing the mask. So you've got on the left-hand side, you have the photolithographic mask. On the right-hand side, you have the delayered, imaged M1 layer that's actually been manufactured. and you can look at the difference. You have the design file, and you have the imaged data, and you see the little red lines on the right-hand side is where the boundaries ought to be according to the design, and then the black and white is where it's actually measured, and the difference file is shown on the right-hand side. So even at the M1 layer, there is a difference between your design and the manufacture. So we're making progress. We haven't got there yet, but we're making progress. So we can pause at this point, and you say, well, I've got a technology now that enables a sort of certified trust. I could randomly sample chips, put them through my X-ray imaging system, and I could issue a certificate. Yes, this chip actually has been manufactured according to a certain standard given that we might decide on. So on the left-hand side, you see the 3D nanoscale rendering of a CMOS design. On the right-hand side, you see what was actually manufactured. So we're doing good so far. So this was back in 2016, but it's not quite there yet. We need to learn more, and we need to deliver more, in particular, scan larger areas. So that was Global Foundries. So let's have a look at Intel. So instead of going to Intel and asking Intel for a chip, we just went to a local store, paid $50, took one of their microprocessors, and imaged it, and said, what can we learn? And the answer is, this happens to be a 22 nanometer FinFET technology. The answer is you can learn an awful lot. You see here at the bottom of this image is the copper interconnect for the transistor layer M1, and then you build up this hierarchy. This is the reconstructed X-ray image. You see the length scale shown here, 500 nanometers. You get an idea of what we're dealing with. And you can fly in and have a look at the quality. Remember those vias that I showed you before from Global Foundries? Well, let's see how Intel does on those vias. And let's fly through. So we go on a trip. Those vias from Intel have beautiful straight sidewalls relative to what we saw before. The roughness, the surface roughness that you see on the metal interconnects is very good, very low. And I can fly through down and go down through this structure and explore in a sort of virtual reality sort of view of what was actually manufactured. So absolutely fantastic. And it turns out that these different manufacturers, I'm going to show you another manufacturer further on, they leave behind a type of manufacturing fingerprint. I can figure out where this came from. I can figure out something about the quality of engineering that's going on. It turns out that there are things about this Intel chip that you can say that the other manufacturers we looked at did not take into consideration. There's a lot of knowledge here that you're accumulating by what? Just doing X-ray imaging. So let's look at some detail in what is currently state-of-the-art FinFET CMOS technology. Let's learn something about it. So again, from a design file, this is a measure of the complexity. Remember, now we're back into a design. And so this isn't the image chip, that's coming later. This is the design rendered in 3D, a little cube of 4 and a bit microns on a side. And you can see on the right-hand side that the thicknesses of the layers are down in a few tens of nanometers. You have vias that are, let's say, 30 nanometers, metal layers that are 60 or 70 nanometers. And down at the bottom, way down at the bottom, you have the actual transistors. So this sort of connectome, how you connect the transistors is part of the intelligence of a circuit, is encoded in this metal interconnect. And we want to explore that. And you can see the different length scales shown here in the vertical, in this rendering. There's also the material properties, which I'm sort of not spending much time on, but there are many different materials used in design of a circuit. There's tungsten, aluminum, copper for the metal interconnects that we've been looking at, silicon dioxide, various dopants, and so on. All of these can be explored and measured using X-rays. Lots of wonderful things about X-rays, but I'm not going to dwell on that very much. I'm really going to stick with the sort of geometry aspects of this. An old-fashioned way of figuring out what the layer thicknesses are is to do transmission electron microscopy. So here's an example, and you take a small slice, again destructive. You take a small slice of the circuit, and you look at it in cross-section. So these are the actual measured thicknesses, not the design numbers, which are different. These are the actual measured numbers in a transmission electron microscope. And remember, what we're planning on doing is doing this for the whole chip in 3 dimensions, not a single slice of some tiny portion of a much larger chip, but for the whole chip. Before we get too excited about that, let's look at a simple circuit. This is a 3D rendition of a design. The design mask is shown on the right-hand side, and the 3D rendering of that. So the 2D photolithographic masks are an abstraction of the 3D manufactured part. So the 3D design is shown on the left-hand side, and the 2D abstraction is shown on the right-hand side. So I'm creating the 3D from the 2D. And then I can color it in and tell you what the metal layers are, and then I can figure out what the circuit is. So I can do reverse engineering, and so this happens to be an inverter. There's a schematic diagram on the right-hand side, which is another abstraction, and there's the 3D rendering of that actual circuit as designed to be implemented. This is FinFET technology and you can see there's a 48 nanometer pitch, and there's a 90 nanometer gate pitch, and then various assignments for various dimensions, including, even though this is a 16 nanometer technology, quotation marks, there are actually features in here that are 10 nanometers, and there's actual physical objects in there that are controlled to deliver things that are 6 nanometers. So even though the manufacturer is advertising this as a 16 nanometer process, there are other things going on that have much greater control than you might have expected. Now you can see on the left-hand side the design in 3D, and then on the right-hand side what the X-ray imaging delivered in terms of that design, colored to tell you how the electrical connections are made and what the function of that circuit is. So you can see reverse engineering is just sitting there waiting for you with this technology. Let's go back and assess where we're at. We actually are missing something. We need to be able to measure large areas, because chips are large, they're centimeters in size, and they're built by a layered process. I haven't shown you how to do that yet. So now comes the next hard part of the talk. We've got this example, this optical photograph of a CMOS test die that I was showing you before. It's got a few hundred, it's got 165 solder bump pads, and it's got a certain pitch and so on. Now, for a large area, you've got this small X-ray beam that you need to scan across the surface and collect the diffraction patterns. And you can do this in 2 ways. You can take the chip sample as shown in the top piece here, and you can rotate it about this axis, omega. The problem with that is, as you rotate the sample relative to the X-ray beam, eventually the X-rays cannot penetrate through the chip, and you end up with a limited rotation angle that you can use, which means that you end up with a missing wedge of diffraction data that is shown here. So the image slices that you take in the Fourier transformed plane, you see these slices, you get multiples of them, but there's a piece that you can't access that's shown in blue. So there is actually a known, better geometry called laminographic geometry. So laminography, where you have to choose an angle with respect to the X-ray beam, and then you rotate around that angle, and finding that angle, the optimal angle, is also a challenge. but you end up not with a missing wedge, but with a missing cone, which means you lose less data. So that's where we're headed. And choosing that angle and how to make this all work, you again go to simulations before you commit to design. And so I wanted to show you a little bit of that. I'm showing you how you can visualize this. The chip is shown here. The X-ray beam comes in, and you can see the angle. And then you're going to rotate this around the z-axis, which is the normal to the plane of the chip. You can rotate omega here. Now, this is actually a synthesized chip, so it's a design. And then the diffraction pattern at the detector, the X-ray diffraction pattern at the detector is shown here, is actually calculated. That's what we got to take the inverse of. Well, just taking one image won't do. If you want to do a 3D reconstruction, you have to take multiple images, just like in regular photography. If I wanted to take a 3D image of this room, I would take photographs at different places around the room. Likewise, I would take X-ray images at different rotations of this chip that you see here. So let's see this in action. We can do this with a little movie. You see the orange or chip, and then we're going to rotate it and look at the black diffraction. The black screen will look at the diffraction pattern. So let's do that. We rotate it. We then bring in the X-ray beam. There it is, going in, passes through the chip at its special angle and creates a diffraction pattern, which I then rotate. And I'm taking, as I rotate, storing up all these images. And typically, there might be 1,000 such images that I need in order to get a high fidelity 3D reconstruction. 1,000 of these things. So that's that. Again, in Fourier space, you're going to have a missing cone of information that is highlighted here in front of you. That's the price you pay for being able to scan over a large planar surface in this laminographic configuration. So in the Fourier plane, you're doing this, and you can see the Fourier images, the diffraction images rotating around that cone. That's how you fill the volume of the Fourier space, except for the missing cone. This has a big effect on how you can do your reconstruction, and you have to add, in order to successfully reconstruct your 3D image, you actually have to add new information into the system. Not very much, but a little, and I wanted to discuss that a little bit with you. So here we have a laminography null space, which is the blue missing cone. The magic angle, by the way, turns out to be 61 degrees. And then the representation of the many, many diffraction images is shown, let me just see, is shown here. This is, let's say, 1,000 of them. So you can see lots of diffraction data in brown, but there's a missing cone. How does that affect the reconstruction? Well, the original image, that synthetic image, is shown on the left-hand side. It's beautiful. You see that big slab of copper on the top, and then fine features down below near the transistors. If you look at the reconstructed image, the big flat surface, because of the missing cone, doesn't look flat. It looks like there's something missing. And so you have to, this is a very interesting effect, you have to add some more information into your reconstruction process in order to fill that in. Here it is again in 3D, the 3D Fourier transform of the original image and with the cone removed. And you can see what it's done, how the information in the Fourier transform has been removed and how it's impacted the image. So it turns out that small features are very well represented and large flat objects are not. So this is a very interesting case where if you do an image reconstruction where you say, I know that this is a planar object, if I don't see the diffraction peaks for small objects, then the object must be flat. So it's one of these cases where if you don't see it, you know that it's there. Think about that. So sort of finishing this up a little bit, 3D X-ray chip scan microscope, a first version was built in Switzerland. Here it is, you see it involves a lot of mechanical work as well as very precision motion stages, and a great deal of experience goes into getting this design right. And that was one of the things that I was looking at when in 2016 I was looking at the people and the quality of the effort. This particular machine has been purchased by the US government. It is now at Argonne National Lab. There is another version of this machine that continues to work and do good work in Switzerland. Here's some data showing a zoom capability where you can scan over large areas. These are the solder bump pads are shown here on that original chip that I was showing you. And if you look at the movie, you'll see there's a marker comes out and measures it. It's 170 microns. And then it'll zoom in to a smaller region and look in more detail about what's going on in there and look for individual transistor circuits as it goes through virtually delayers without destroying the chip. Goes through those layers, which are now used to this sort of connectome, and goes down to the lower layers. And there's your M1 layer with the railroad tracks about 500 nanometers apart. Now we're going up through the layers and then back down again. And then we're zooming in on that inverter design that I'd shown you before. And you can then build a schematic out of what you're seeing in 3 dimensions here and say, there you go, that's the electrical functionality of that versus my 3D rendition from the original design. And now just doing everything backwards, going back through the chip. You might ask, what all these layers mean, and I can explain that some other time, what they're there for, what function do they perform. The point is that on this large scale, you can have a microscope that goes and looks inside the chip in 3 dimensions and tells you what was manufactured relative to the design and tells you what the circuit function is in the system. That's pretty good. Looking back at the M1 layer, it's sort of extraordinary to me, so I love this movie, that you can see in 3D, virtually delayer down to the M1 layer and look at that. You're just flying through the circuit design of the actual manufactured part of that M1 layer. It's like, wow. And you can go back and look at many times as you like later because you haven't destroyed the chip. It's sitting there waiting for you. So that's beautiful. And then here's another picture of it because I love it so much. It's my baby. Now, you can take that M1 layer and you can apply you can say, let me look for features that are not supposed to be there. And so let's look to see what it is. I do some image signal processing to threshold it, the X-ray, delayered X-ray image. And then I look at it and check first the topology is correct relative to the circuit design. It's a very important step. And then I go in and say, well, is this actually what I designed? You notice it's not very straight lines. It's got sort of defect. That's all to do with the quality of the manufacturing. And there's a lot that you can learn about the instruments that are used by the manufacturer and the quality of those instruments and so on, the processing. We can say more about that. So you can machine-generated delayering of the M1 layer and look at the threshold landscape that you've got here, and then you can put in a defect deliberately and see if it'll detect it, and of course it does. So you have a way of verifying design and manufacture. So let me just finish up on this statement. Again, the team is very important. I've got a method of pursuing trust. I wanted to emphasize just what an extraordinary achievement it is to have this ability to control manufacturing at the nanoscale that is what gives us the electronics that we have today. On the left-hand side, I show you a handprint from 27,000 years ago in a cave in France where a human achievement was the beautiful art that was done in those cave paintings. Since then, we've had language, theater, music, mathematics, and I want to add to the list nanoscale manufacture of chips with billions of transistors per square centimeter, with a technology that has elevated us from into a new realm. That's the end. Thank you.
Thank you, Tony. We have time for question and answer period.
Yes, as Bruce said, I am a member, and I love the pictures, but my question is, if I gave you a commercial chip, like the one in my pocket, how long would it take you to image it? And what are the technologies that are limiting that speed you can image?
Right. Excellent that you bring that up. It's a question of what resolution you would require. So lower, meaning less resolution, would enable you to scan the chip much faster. If you want to zoom in detail and look with a few nanometer resolution, it takes longer, and it's limited by the flux in the beam. So there is an upgrade technology that will increase this by at least 2 orders of magnitude. In other words, the scan time will be reduced by at least 2 orders of magnitude for the highest resolution. So it's moving along in the right direction.
Yes, this question comes from Robert Yeager of Seattle, Washington, and he also was curious about sort of the rate-limiting steps in the technology. I don't think in that previous answer I heard an actual number as to how long it takes to scan these things. And then the other question is, are there any resolution limiting factors to be aware of?
The actual numbers on the data that I showed you, you can get 16, on the existing system, you can get 16 nanometer resolution for the area that you saw in about, in between 24 and 48 hours. With the upgrade, that will be, you would expect that to be very much a shorter time period. On the limiting, so you can increase flux to reduce the time period, but if you increase the flux too high, you will eventually end up with damaging the sample. And the reason for that is that you start depositing charge in the sample and it starts damaging it. Right? So there's this trade-off. And why the zoom microscope was built was so that you could scan very rapidly at poor resolution, find areas of interest, and then zoom in and spend your time, your precious beam time, on that. Is that better for you in terms of a more complete answer? I hope so.
Yes.
Okay, very good.
Take the red microphone. Please stand up, tell us your name if you remember.
My name is Timothy Thomas. I'm a member of the Philosophical Society of Washington. I wanted to ask about, one of your goals is the detection of malicious changes that are introduced somewhere in the process. But from the way your part works, it works from the section of when the design is finished to the time it's manufactured. Correct. Whether or not there was been something introduced then would seem very difficult to introduce a change in a foundry with all those people, and yet introducing a change to the design would be quite easy.
Yep. So I haven't touched on the malicious activity in the design process, and I won't talk about that. That's been addressed by other people. What is unique and new is the way in which we've addressed the physical, actual manufacturing piece. And I would counter that, yes, it is rather possible to introduce malicious manufacturing steps into the process of manufacturing the chip. Let me give you a concrete example. I showed you some metal layers that had thicknesses that were tens of nanometers in thickness. If I were to take some of those metal layers and thin them, I would effectively be introducing a type of fuse. If the chip was operated normally, the fuse wouldn't blow. If I did something to cause the fuse to blow, all my chips would no longer be functional because I reduced the thickness of a given layer.
What I'm concerned about in that scenario is I once toured Intel's foundry in Arizona. It's quite an impressive no, it was in New Mexico. Quite an impressive thing. It's kind of hard for me to imagine one of these little drones in these suits, you know, that you have to wear, going in and saying, you know, it's like you change it to 3 and nobody else noticing. And there's a lot of people working on that.
My concern the concern is not so much in the US, it's in some other place outside of the US.
And the is actually introduced by the management of the factory, not by the employees of the factory.
By the software that drives the deposition process and so on. It's just an example, but there's many others.
But then, okay, but the manufacturer then is actually intending that it do that.
The manufacturer might not intend it, but it happened in his shop. Who else?
Okay, well, we'll take one from Zoom participant, Maria Zemenkova.
Okay, I just really love to talk because in my experience, most of computer science, imaging, tomography, etc., is turned towards medical fields and some other fields of science. So I love being turned towards computer science. But since I am a computer scientist, I just wonder how your fantastic work actually helps in certifying or discovering in reverse engineering what the chip actually does, or if we have the design and then you can image it, whether the design is actually properly manufactured in the chip.
Right, so that's what the bulk of the talk was aiming at.
Yeah.
Right, comparing design intent to what is actually manufactured.
Yeah.
There's many other things that are possible. Reverse engineering the actual circuit design itself, the functionality of the circuit, what it does. Suppose you have a chip, you don't know what it does, you can figure this out. and there's a lot of other things that are possible.
I mean, to what certainty level?
We've only done this for simple, relatively simple circuits, which we're very sure about.
Okay.
So
But
you know that your
way to go. Fantastic.
Yeah. So So what I've described today is proof of principle, and a step forward relative to what has gone before.
Yes. Wonderful. Thank you so much.
Hi, my name is John Tristan Ritland. I am not a member. One thing I just wanted to add, the gentleman all the way in the front mentioned the possibility of defects being introduced in the manufacturing process seeming a little bit strange. One anecdote that I have heard, and I don't know if this is a real thing or if this is just a rumor, but supposedly one of those Intel foundries actually had a serious problem where they were chasing every now and then one of their ovens would have a very high water vapor pressure, and it would be sporadic, you know, once every few months. It would just show up and they'd have a high water vapor pressure, and it would take them a lot of time to pump back down to high vacuum. And it turns out the reason eventually was discovered. One of the janitors had discovered that it was in fact an oven and could in fact reheat pizza. So
I suspect that's an apocryphal story.
you know, I did I was also curious, can your technique tell the difference between the different materials?
Good question. I'm glad you asked that. The answer is...
Or even, sorry, even further, just different doping levels.
Yeah, excellent question. So of course we have worked on that. What I've shown you doesn't show that capability, but there are two techniques that can be used. One is to tune the edge of the X-ray through the edge of the material. So there's X-ray edges. So for copper, you could tune either side and do a difference, proving that it's copper. And for other materials, you can do the same thing. So that's type of spectroscopy, telling you where the material is. There are other ways that you can, in terms of modeling, when you're simulating, if you have a model, you can simulate what the X-ray image ought to be if it goes through a certain amount of silicon dioxide and a certain amount of copper, and you can figure out, because you've taken all these images, you can figure out whether it really is silicon dioxide and so on. In terms of doping, typical doping levels in modern transistors can go down to a part per million, and that you can get with X-ray fluorescence, though at lower resolution. So this particular microscope was designed to accommodate X-ray fluorescence spectroscopy, but at a lower resolution, so that in principle you can detect the doping type and level in modern transistor topology.
So this is from Jim Tallons of Boynton Beach, and I think he's interested in the general question of, have you actually found any malicious manufacturing defects, whether yourself or perhaps you've heard of other cases?
The other case, okay, so we have not, in the chips that I've shown you, found anything malicious. There are other situations where bad things have happened because of lack of control of where things came from.
So I have a question for you. So it takes a day or two to do this scan on a single integrated circuit?
Yep.
And let's say your manufacturing run is 10 to 50 million
Right.
integrated circuits. How do you deal with the issue of intermittent, well, basically what kind of sampling do you think you need, and how hard is it to introduce defects? I'm talking about malicious actors here.
Oh.
Introduce defects into only some of the chips.
That's a good question about sampling, and I don't have a proper answer for you. It's the way you've posed the question, it's sufficiently complicated. It needs a careful thought. In other words, other techniques would have to be used to filter prior to committing to the rather expensive chip scan that I've shown you.
And how does this coordinate with functionally testing the chips? Just take them out and just run them too hot, run them too fast.
Yeah. So that's a very conventional way for screening for defects, and this would be the X-ray chip scan, being more expensive than that, would be downstream from that. So there's a sequence.
So once you find out there's something wrong, this can help you find out exactly what it is.
Absolutely. Which is the way it's done at the moment. There's a hierarchy. Before you commit to more conventional techniques like the mechanical delayering that I showed you at the beginning.
And what are the prospects of speeding this up?
As I mentioned earlier, speed up will come from increased X-ray flux, which is an ongoing upgrade both at Argonne National Lab and at the Swiss Light Source and in other places around the world where there's at least 100x, and actually more than that if you improve the some of the X-ray optics that's used.
What do you think constrained by the intensity of the flux degrading?
If you want high resolution, you're going to have a trade-off between the amount of damage you get. If you want to do a quick scan of the complete chip, it'll certainly help that. With low resolution, of course.
And we were talking earlier, these are done in air,
Yes.
not in a vacuum. And you could potentially do a living cell or something like that.
Well, they'll be dead. For the biological.
It starts out living.
Yeah. For the biological samples, the way you would proceed there is you would freeze it and put it in a vacuum. It would be frozen in a vacuum. And that's to limit, the biological samples are much more fragile. So you'd limit the damage with that way.
I know you're a chip guy, but are you talking to any collaborators about perhaps doing that, since there are apparently only 2 of these machines in the world?
We're not going to do it for this machine, which is designed specifically for chip scan. But going forward, there might be the possibility of making a new machine that would have this low temperature capability.
But you can't just put a cryogenic stage on there?
No. The amount of engineering that has gone into this, and I deliberately pitched this talk in a particular way, the amount of engineering going into this is not insignificant. There's also a bit of physics, and there's a bit of image signal processing, and there's a whole team, a whole ecosystem that you have to build to make this happen.
How much storage and signal processing power do you need?
A lot.
Are you running this on Frontier or something that can have more local?
The way these were done was with Intel processors, which were, in order to get the performance up, there were pieces of the code that were machine code. I mean, it was a tough job.
Murthy Palwarapu, member here. So we talked about trying to find the things bad people could have done, but is it possible that this technique could be used by the bad people to figure out the designs of our designs?
It could be used by us to figure out the designs of other people, yes.
No, but how,
Yes.
so how is this technology protected?
This is all available for people to explore themselves. We haven't done anything to hide. Of course, there's lots of secret sauce that only comes with experience, but we haven't done anything to deliberately, obfuscate what we're doing.
I think there's also a lot of manufacturing trade secrets and know-how that is required to run a fab that can make these things beyond just knowing how they're designed.
Well, the interesting part is you can actually see the personality of the foundries that these chips came from. So in some sense, I can tell you where it came from, what the designers were doing, what the manufacturers were doing, how good they are, and various other metrics, depending on what your interest is. For example, some chips are more radiation hard than others, and you can see it. Yeah, so there's a lot of information here.
How many chips have you looked at?
Quite a few.
Quite a few?
3 manufacturers, Global Foundries, Intel, and another manufacturer I'm not going to mention.
Have you been working with them? Or, I mean, have they come to you and said...
With Global Foundries, we have worked with Global Foundries.
Right, but not the others?
Not the others, no.
Ah. Are there any other questions?
So my name is Jalen Menser. I'm not a member. My question is, looking forward, say, 20 years in the future, do you expect this technology to become increasingly scalable and we'll see a lot of places doing this kind of imaging? Or are the fundamental limitations of the materials needed so intensive that this will remain a somewhat limited but powerful technique?
It's an excellent question. As I mentioned earlier, what has really been shown to you is proof of principle. And it really depends going forward on a number of factors. If the technology, as we've shown, is feasible, and there is a path forward to more sophisticated exploration of what this combination of materials and geometry is capable of, the question really resides in whether there is going to be a requirement going forward of some sort of certification that certain critical components be assured of their fidelity. I think you understand, being in Washington, D.C., you understand what I'm saying.
We do have another question, actually, from a Zoom participant, Maria Zemenkova. Maria, can you unmute your mic and ask your question? Thank you.
I know that it was mentioned that in order to examine living organisms, they would need to be frozen. But suppose they do not to be frozen, would it be possible to actually examine protein folding in real time, which is a very important problem in biological and medical sciences, and lots of people are working on protein folding.
Right. I think it's best that I don't comment on that. It's outside of my expertise. So in general, I think the answer is no, but there may be, you know, like any good sort of engineer, when faced with a problem, there may be a creative solution that we might be able to come up with.
Okay, good.
I'm sure there will be. Thank you.
Maybe.
That's a good place to end. Let's thank our speaker for spending time with us. Thank you, Tony.
Thank you for your patience.
Before you go, we have a few closing remarks. The next meeting will be the 2468th, and it will be on December 2nd, and the speaker will be Sean Gulick. Sean is at the University of Texas, where he is research professor in the Institute for Geophysics, co-director of the Center for Planetary Systems Habitability, and associate chair of Lithosphere and Deep Earth Studies. And he'll be speaking about, colloquially, the latest on the great dinosaur extinction. This lecture is sponsored by PSW member Erica Kane. The 2469th meeting, which will be the last of fall 2022 and the last of 2022, will be on December 16th. The speakers will be Brett Denevy and Wesley Furman. Brett is planetary geologist at Johns Hopkins University Applied Physics Laboratory and Lunar Surface Innovation Initiative Lunar Surface Lead. Wes is senior staff scientist at Johns Hopkins University Applied Physics Laboratory and Lunar Surface Innovation Initiative Lead. They will be speaking about the Lunar Surface Innovation Consortium and about going back to the moon to stay. We don't have a sponsor yet, but I hope by then we will. If you're interested in sponsoring, please see me after we adjourn the meeting. Please check the PSW website often for up-to-date information on meetings. And before we go, let's thank the people who worked hard to produce the meeting. Janet Soreth for reading the minutes. Robin Taylor, video, sound, live stream, and Zoom. She's in the back where you can't see her there, but she makes it all work. Robert Thompson and Lloyd Mitchell for running the cameras. Erica Kane in the front here for taking care of the live stream chat. And Bill Mitchell, who you can't see, who will edit the video. And with that, I will ask you to return your name badges to the plastic bins in the back, and I will adjourn the 2467th meeting of the Society. And I wish everyone a good morning, afternoon, evening, or night, wherever you are. The meeting is adjourned.